the same happens with the LEDs. There is not a unique configuration that create the best performance. Okay, so it depends on the application, it depends on the scenario, and depending on that, we should select one kind of receiver or the other. Okay. And once the signal arrives to the receiver, we have to amplify the signal. Okay, as always. So there are some ways to amplify the signal using different amplifiers. Basically, the most important of these two. We will see this one, which is not the most important, but it's the most typical one. And let's talk about the low impedance and high impedance amplifier. We have to find somehow a trade-off between these two, because the larger the impedance amplifier is, the lower the thermal noise is, and the sensitivity increases, which is good. But also, we are decreasing the bandwidth. So we can use an equalizer at the receiver side in order to equalize the channel, but well, still we are decreasing the bandwidth, which is bad. Okay. However, okay, we have very good pros here, but with an impedance amplifier which is low, we are increasing the thermal noise, and somehow in some environment this thermal noise is predominant. Okay, so we have to be careful of that, because if the thermal noise increases a lot, the system becomes impractical. Okay. And the most typical one is the transimpedance amplifier, which is converting the input current into an optical, into an output voltage. And they are the most used because they find a balance between these two characteristics here, okay, between the sensitivity and between the bandwidth, okay. Okay, so of course we are using VLC for communicating, so it's very important to detect which properties of the photodiode are useful for communication purposes. So the photocurrent that is generated by the photodiode is proportional to the received optical signal. Okay, this proportional is thanks to this responsivity of the photodiode. That is a characteristic of the photodiode, and as we said before, this is measured in amps per volts. Okay. But we can use some extra elements at the receiver side. Okay. For example, we can use an optical concentrator that whose path losses can be modeled by using this equation here, where we have a refractive index here, and also the field of view angle, which is a characteristic of the photodiode. Okay. And also we have a variable here, which is a Boolean, which means that if the incident angle is larger than the field of view, we are not receiving any signal. Okay, so we have to be careful with that, because the larger the field of view, the most probable is to receive the signal, but also we are increasing the interferences. Okay, if we are working in a dense deployment, so we need to be careful with that. And also we can use an optical filter in order to eliminate signals that are out of the desired band. Okay, so typically, well, most of the prototypes are using a blue optical filter because they are using a phosphor-coated LED that has a blue LED chip, and they are eliminating the phosphor part, okay, of the spectrum. And the reason is that the blue LED chip has a larger bandwidth than the phosphor part. That's why we prefer the blue wavelengths. But also we have to be careful with that, because we are decreasing the optical received signal. Okay. So now, how the front-end devices affect the end-to-end channel? The optical wireless communication channel is typically modeled by two effects. One is the front-end devices, and the other is the free space channel. The front-end element, as we said before, act as a low-pass filter. Here I have included, thanks to this source here, I have included 4 models of 4 front-end devices, and we can see here as they are working as a low-pass filtering, okay, with 3 dB bandwidth of tens of megahertz. And it is characterized by this parameter here, which is a parameter that characterizes both front-end elements. And the free space channel is modeled by using this equation in which we have a line of sight part and a non-line of sight part. Okay, the line of sight part is computed by using the radiation pattern as I explained before. Also, some part of the photodiode, and don't forget here this Boolean here, and keep in mind that we have the area of the photodiode. So the larger the area of the photodiode is, the better the performance is. But also keep in mind that the larger the area of the photodiode, we are increasing the larger the capacitance is, and then the lower the bandwidth is. Okay, so also we have to find somehow a balance between these two. So a possible solution to be done can be by using multiple photodiodes in order to build an equivalent area of photodiode, but not increasing this capacitance that is decreasing the bandwidth. Okay. So of course we have several noise sources. These are the 4 most typical ones. We have a shot noise, thermal noise, clipping noise, and some interference from other access points that are not they are not noise but interference. Let's say that most of them can be modeled as additive white Gaussian noise. I think that most of you know what is it about. And the shot noise is produced by fluctuation in the number of photons when it is arrived to the destination. Thermal noise is produced by the thermal agitation of electrons in the received circuit. And the clipping noise, as we explained before when we were explaining the nonlinear transfer function of the LED. So when we are working with a signal that is larger than the dynamic range, we have to clip the signal in order not to saturate the LED, and it produces some clipping noise. So I'm not going to go into details for equation, but just keep in mind that the shot noise is produced by artificial light and also the ambient light that is coming from the natural source, multiplied by these two are the power spectral density, and this is multiplied by the electrical bandwidth. Okay. The thermal noise is used by using this Boltzmann constant with the absolute temperature of the receiver circuit and also the load resistance. And by assuming these 3 noise sources, we can compute the total power spectral density. Okay.